I'll just give it 1 or 2 minutes to let everyone come in. All right, we might make a start while everyone's filing in. So, hello everyone, welcome to this session. I'm Sam Stranks. I'm a University Assistant Professor in Energy at the University of Cambridge. And I'm going to talk today about some of the work we're doing in our research group and work that's going on in many other groups around the world on halide perovskites, particularly for photovoltaics and lighting. And what I'll do is I'll encourage you to put questions into the Q&A along the way. I'll give you an overview of the topic and the subject, and then at the end we'll have time for the questions, but please do put them in as we go along. I want to start by just giving context to the potential of solar power and solar photovoltaics. And if you think of this cube representing how much sunlight's hitting the Earth at any one time, so 200,000 terawatts, then this represents our global power demand. So you can see, so I'll just see if my pointer's coming up. There we go. So you can just see how much potential solar power has to cover all of our demand. And in fact, if you look at our current PV installations, it looks like a tiny speck in. It's just under 1 terawatt. This is a lot of PV, and we're doing very well in terms of deploying a lot, but it does show that we still have a long way to go. One of the exciting things really that we've seen is that solar deployment is growing very fast, and you'll see that solar panels going on rooftops and solar farms, and this is fantastic. We need this for decarbonisation. And so this plot is showing the projections that the International Energy Agency puts out each year. These are showing these different coloured plots here of how much solar power or how much solar photovoltaics are being deployed. And the black data here shows what's observed and what's actually deployed. So what you can see is year after year consistently, they underpredict by a long way how much solar could be is going to be deployed in the given year. And that trend has continued and continues still today. So this just shows us how fast we're putting it out. It's faster than the IEA could actually predict. And the reason for this is that the cost of PV, particularly the module price, has dropped significantly over the last several decades. So we've seen a factor of 100 times drop since 1980, and in fact another factor of 10 drop in price since 2010, which is staggering and really is what's driven this rapid deployment. And this has been really due to two things. One is that economies of scale, as more volume is being produced, as more panels being produced, there's cost reductions in the materials and the manufacturing, but also R&D efforts. So research and development, which means that the power conversion efficiency, so how much sunlight we can convert to electricity, how efficiently we can do that, that's been improving consistently as well. But the problem is the current PV technology, so those that we rely on and really dominate the market, and I'll talk about that in a few moments, these won't get us all the way there, won't get us to the levels that we need to get significant decarbonisation. Almost every decarbonisation model puts solar photovoltaics as one of the really leading energy sources that we need to rely on. And so just in terms of what the limitations are of the current technologies, one is that it's not just the cost of the panel itself. So if you think about the panel, but there's also the system, there's all of the other things, there's the installation, the wiring, the inverter. These are called the balance of systems costs. And these costs are much harder to bring down. And in fact, this is a plot showing the cost of modules, so photovoltaic solar modules over in Germany over sort of the course of around a decade. You see the module cost has dropped, and that's actually continued to drop. But then there's these other costs, these balance of systems costs, which are now, in fact, dominating the system cost. And so this is much harder to bring down unless there's a really big, for example, big efficiency jump in the performance. Another issue is that most of the PV panels that are made today, they're made of crystalline silicon, and this is you need very high temperature to process silicon to ensure there's no defects and problems with the cells. So this means that factories tend to be very expensive to build. So there's lots of very high capex associated with building new factories to make more solar. And there's also issues because there's only a few places geographically around the world that manufacture these panels. So there's been, particularly through COVID times and also more recently, there's been supply chain and also geopolitical issues. So this is really limiting our ability to really hit the levels that we need to hit to reach decarbonization. And in fact, those levels need to be something like a terawatt per year deployment by the end of this decade, which is actually, in fact, more than we've produced to date. So that just shows the scale and just how much PV we need to produce. So these issues are limiting the rates of deployment and also potential applications as well, because silicon is quite bulky and it limits what you can do. And I'll show you in a few moments some of the other opportunities that could come with other materials. So what we need other solutions with higher efficiency, more modularity to do more things with it, reduce costs, and also new manufacturing paradigms where we could manufacture at much higher throughput and at much lower cost. And I'll talk about a lot of that in this talk. So the current technology where we're at today, so I mentioned that crystalline silicon is what we see. So when you look on many rooftops, the majority of panels, 95% of the market is crystalline silicon, these sort of blue looking panels here. It's a very good technology. It's been developed over many decades, and it will last for a very long time on the rooftop. So it really has come a long way. And if we unpack this PV module and PV system, what we see is that, sorry, my mouse is a bit clunky. On the left, you can see this is the cell. So we make the silicon ingots are cut to make cells, and that's shown on the left there. That's a wafer of silicon. And then these cells are strung together to make a module. And then, so that's a panel. And then in many solar arrays, these modules are then joined together to make a solar array, as you can see in the middle here. There's another slightly different technology, that thin film technology. I'll talk a bit about that today, where it can be produced instead of in small cells and when you're limited by ingots, you can produce one big panel in one production step. And so if you look at a PV panel, these solar cells and the module is then encapsulated typically with glass and other encapsulation materials so that they can be protected from the environment and last on your rooftop for 25 years plus. In terms of how a solar cell works, so this is here where we're looking at a cross section of a solar cell, so we're cutting it in half and looking at the side of it. And so in its most simple form, what you have is that you have something that absorbs light really well. So a solar absorber layer in the middle. This is this black layer that I've got in the middle here. And that's sandwiched between two electrodes, an anode and a cathode. And if we shine light on it, what happens is that absorber layer absorbs the sunlight, and that energizes electrons. And those electrons, once they're energized, can then be transported through the cell and be collected as current. And this is the principle of how the solar cell works. That current, we generate both a photocurrent and also a photovoltage. And that means because we've got both current and voltage, we're generating power, and that can drive an external circuit. And there's one other subtlety to when we energize electrons. What we do is we leave behind where the electrons come from. There's actually a particle called a hole, which is left behind, and that's a positively charged particle. And we have to also transport that to the electrode as well. We have to consider transport of both the electron and this hole. So if we run this, if we absorb light, we energize these electrons and holes, and then they are collected as current, and then they drive an external circuit. So for example, this light bulb here. I'll play that one more time. just to run that through. So these electrons and holes are transported. So what we need for a solar cell material is we need it to absorb light very well, and we also need it to be able to transport these charges really well. They're two important criteria. And along the way, those charges may hit things like defects or traps, where those electrons could lose their energy to heat, for example, and those are unwanted things in the system. And I'll talk a bit about that towards the end and some of the things we're doing to address those issues. So when we think about solar cells, we think about the solar spectrum. So here, this is actually what the solar spectrum looks like. This is looking at the wavelength. So it peaks somewhere in the green, but there's lots of light in the near infrared, which is also coming in, and we ideally want to harvest as much of that light as possible. This is what the spectrum looks like on Earth. You have some absorption from the atmosphere, from water molecules and oxygen and various other things. So that's why you have these small dips here. But that's the solar spectrum, and that's what we want to maximize how much light we can harvest in that spectrum. And so when we think about our solar absorber layer, we need to think about how we can absorb a lot of this light. And these are semiconductors, so they have what's called a band gap. So that we have to energize electrons across that band gap, to give it at least enough energy to energize across that band gap. So often for a solar absorber, when the infrared light comes in, we don't have enough energy to energize those electrons. And so in fact, that light isn't absorbed, and then that then transmits through the cell and doesn't contribute to produce electrical power. But on the other hand, if we give it high enough energy light, so blue light, for example, we have more than enough energy to energize an electron, and that is then energized and now is in the conduction band, so now it can conduct really well, and then it's conducted to an electrode and collected, and meanwhile, if you recall, I mentioned about this hole, that's also collected in the other electrode. So this is the working principle of the solar cell. We want to maximize how much light can be absorbed. There's a bit of a trade-off because we want this band gap to be as small as possible so we can harvest as much light as possible, but then that impacts our voltage. So there's a bit of a compromise where the actual efficiency ends up being some compromise between the two. So we can't have too small a band gap in the end. But that brings me on to the perovskite materials, and these are the materials that we're working on in our labs. And so the perovskite family of materials, actually, it's a huge family of materials, and it's anything that takes the crystal structure ABX3. So when we think about the atoms or the ions and how they're arranged in these materials, they can take an ABX3 crystal structure. This is actually named after calcium titanate, which is a naturally occurring mineral. And there's many, many different perovskites naturally occurring, many minerals. In fact, it's one of the most abundant material families in the Earth's crust. But the materials we work on for solar cells and for lighting, these are man-made versions. The compositions aren't those that we find naturally. So typically we have, when we think about the A site here, and so, or just to look at this crystal structure, what we have is essentially we have an octahedron of this B metal sitting at the center, and then these X sites, the X sites is around an octahedron, and then we have these little A sites sitting at the corners of these octahedra. And so when we think about the solar cell materials, at the A site, usually we have small organic cations. These are small organic molecules that contribute here, or cesium as well, cesium ions. In the B site, the metal, we have typically a cation such as lead or tin, and in the X site we have halide ions, so iodine or iodide or bromide typically. And so these are the typical absorbers or emitters that we are working with. And the reason they're creating a lot of attention is because of their efficiency in solar cells. We're seeing huge improvements over a very, very rapid, short period of time. And so this is a plot that shows the power conversion efficiency of solar cells. So this is looking at how much sunlight energy is converted to electrical energy. And this is over the decades. And you can see silicon there is, it's improved gradually over many decades. And this is partly because of developments in semiconductor chips as well that have contributed here, and also just very good R&D that has contributed to these improvements. But you can see the perovskites, since the first reports in solar cells in 2009, have really shot up. And in fact, now they're just as of the end of the start of this year, in fact, they've hit 25.7%. And it's likely that they'll approach the value of silicon, perhaps even later this year, which is a really exciting time. And one of the reasons they're particularly exciting from a scientific point of view is that we can process them very crudely and at low temperature. If you remember, I told you how for silicon cells we have to heat them to very high temperatures to get rid of defects. With these perovskites, they seem to be very tolerant of defects. We don't have to heat them very high. And this is, in some ways, it's very counterintuitive that we have defects in these materials, but they can still work very well. It goes against what we typically teach, that make a very good semiconductor, there has to be very crystalline with very few defects. These perovskites actually, in some ways, are rewriting the textbook in that regard. So when we process these materials, what we do is that we typically have inks of these. We dissolve the salts, the precursor salts that make up these ionic materials. And so in the center here, I've got an image of this ink being dropped down onto a glass substrate, and then we spin coat them in the lab at a few thousand RPM, and this forms a really nice and uniform film. You can see in this yellow image on the left here. And then we heat them gently. So we heat them at 100 degrees Celsius, which is very low temperature for semiconductor processing. Silicon, for example, is more like 900 to 1,000 degrees Celsius or more, depending on what you're processing. So this is very low temperature, but it produces a very nice crystalline film that absorbs light very strongly. And this is the basis for the solar cells that we make. And because this can be done at low temperature, it means we can think about processing them on plastic, for example, or on other flexible substrates, and processing them at much higher throughputs. So processing roll to roll, for example, you can think about a bit like newsprint, a newsprinter, and really printing them at very, very high rates. And this is actually an example of a prototype roll-to-roll printer of perovskite cells. We can see on the left here the yellow of the precursor films, and then they're gently heated, and they form these brown, very dark absorbing cells on the right there. And because, as I said, because they can be processed on flexible substrates, we can make very, very thin cells, and they also absorb light really, really well. In fact, much, much better than silicon. So, for example, a silicon cell, typically we need to have a thickness of something like 200 micrometers or close to 200 micrometers to absorb enough of the sunlight. A micrometer is a thousandth of a millimeter. So this is already quite thin. But then when we go to some of the other thin film technologies, we see this is one which is cadmium telluride, which is 4 micrometers. But when we go to perovskite, we only need 0.5 micrometers to absorb almost all of the incident sunlight, which is extremely thin. For reference here, this is a human hair, which is 100 microns, and a red blood cell, which is 7 microns. And this perovskite cell, you can see, is extremely thin, and that's enough to absorb the sunlight. And this means that we can make extremely thin and flexible and even lightweight solar cells, which I'll talk about in a few moments. We can also change the properties and tune the composition, so we tweak the composition of these materials, and we can actually change the color that they absorb or that they emit. And so this is an example of if we have a pure iodide, if we think about the halides. If you remember, I talked about one of the components being a halide. This is the iodide, and if we mix in a little bit of bromide, we can actually change the color all the way around to, for example, this yellow, which is a pure bromide system. And this opens up applications in colored photovoltaics, for example, so we can integrate these into buildings and actually design them into the facades of buildings, for example. And there's a big a growing area of this building integrated PV where this can be very applicable. But because we can change the color, one of the most exciting opportunities for these cells is actually to push to higher efficiency. And so I talked briefly about that there is a compromise for an efficiency limit, and in fact that efficiency limit for just one absorber ends up being around 30%, or so the thermodynamic limit for conversion of the sunlight to electricity. But we can do a trick where we can actually layer 2 cells together. So this is what's called a tandem solar cell, where we have a top cell which is harvesting the bluer wavelengths, so the blue and some of the green gets absorbed by this top cell, and then the redder wavelengths pass through to the bottom cell, and they're absorbed in the bottom cell here. And these work in series, so actually this combination here pushes the efficiency limit from something like 30% actually to more like 50%. this is a huge boost in terms of performance. That's the thermodynamic limit. When we think about practical efficiency limits, that's more like 35% for these cells. And it doesn't sound like much, but when you compare that to silicon, which has a practical efficiency limit of around 28%, that's actually a huge improvement, a huge increase in terms of how much power is generated over the lifetime of a panel that would last for several decades. And also, given the knife edge economics of PV, it'll be very much a game changer to produce cells that are this efficient without adding any extra cost or even having cheaper cells. Just to mention, one of the slight variations of this is in fact actually putting a perovskite cell on top of a silicon cell. This is also a tandem cell. So we're here that the perovskite cell absorbs the blue wavelengths and then the red wavelengths pass through to the silicon cell. So here you can think about boosting the efficiency of the current technologies. And so you could get something like an efficiency boost from modules today that are around 20% efficient, perhaps up to 25 or even 30% efficient as a full module. But this high power that you can get with tandems, you can also combine this with lightweight, and this actually opens up a number of applications for PV that just aren't possible with silicon at the moment. So thinking about flexible solar cells, and this is actually some work that we're commercializing. I'm a co-founder of Swift Solar, commercializing really high performance tandem perovskite cells. And so this opens up applications in this sort of wearable PV, but also cheaper installation regimes. So what we can think about rolling out rolls or spools of PV, which is much cheaper to install on rooftops than without having to rack them, for example, on rooftops. There's also applications in space and also aerial communications, which are both are growing areas. But one of the particularly, I think, important applications is in electric vehicles, so boosting the range of electric vehicles. So here, a requirement for putting PV in a rooftop is to make sure you're not adding much weight. So really the watts per kilogram, how much electrical power you can produce for every kilogram you add of the panel is really important. And these flexible, lightweight, but high performance cells can be really, really important here. And so in fact, if we think about the range of electric vehicles and how much we could boost, so typically you could get a boost in range of about 30 miles, for example, which is a typical commute for many people with one of these high performance cells. So this will be a growing area as well as these technologies progress. So there is some commercialization happening. There's several companies that are now in pilot phase and actually have pilot lines to produce PV cells and even moving to larger manufacturing lines. So Oxford Photovoltaics, for example, has 100 megawatt line in Brandenburg in Germany, and there's also Microquanta Semiconductor in China has a large manufacturing line as well, similar to 100 to 200 megawatts. There's some products coming out of Solvent Technologies in Poland, just to have a few examples. And our company Swift Solar is starting to produce some products as well. So it's a really exciting time to see this technology, which has started in the labs, now really coming into to be commercialized. And the other part I want to talk about this talk is actually lighting in LEDs, and in fact, an LED is actually just in a solar cell run in reverse. So instead of in a solar cell, we have sunlight, we put light in, and we get electrical power out. In this case, we're actually putting electrical power in, and we get light out. So it's in fact actually we can run a solar cell in reverse, and it can act as an LED. And so because these materials actually absorb light really well, they also emit light really well. And so there's lots of very interesting applications in LEDs and in lighting. Lighting is also another part of our decarbonization that we need to address. Lighting does contribute to a lot of carbon emissions. So, for example, 5% of worldwide greenhouse gas emissions are from lighting alone. And so these are some examples of these perovskite different inks that we can make of different colors. We can tune, again, changing the composition or moving to nanoparticle type systems. We can actually change them to have different emission colors or either as solutions, as inks, or as films. And we can put electrodes on these and operate them as LEDs. And these are a few examples here of blue and green LEDs where there's some really quite efficient operation, which is quite an exciting application area. And because one can make very high color quality LEDs with each color, this opens up a lot of applications in displays, for example. So You will have seen OLED displays, for example, they're using organic materials. Some of these perovskites could actually even surpass those in terms of the color quality they could produce, because they have very narrow and very sharp color emission spectra. And also flexible, again, some of the properties I talked about before, these properties can translate over to LEDs as well, and also very efficient and more modular white lighting. A lot of LEDs at the moment, the white light they produce isn't that nice. So here we can actually fill that gap and really make very high quality white light. So I've talked a lot about the promise of these materials, but I really want to also emphasize the challenges, of course, that facing these materials. They are a new technology, and it does take time to develop these technologies to make sure that they're not only commercial, but they also hit the scales that they need to hit to contribute to decarbonization, for example. And so these are some things that we're working on in our lab, and others around the world are working on as well to really push these materials along. I'm going to give a few brief examples of three of these, and there's of course other areas to work on as well, but I've highlighted three today. So one is how do we take these efficiencies to these limits? I talked about this 30% limit, or even with tandems up to above these more traditional limits to 35% plus, for example. A lot of the work we do in the labs, they're at small scale. We make prototype cells that are sort of 1 inch square, a few centimeters by a few centimeters, for example. How do we push these, of course, to larger area as well, and particularly towards even the module scale? And finally, one of the really important things, how do we make these devices reliable and long-lived? At the moment, the benchmark for silicon cells is 25 years, and many of them will last for longer than that. So it means there's lots of industry standard tests that have to be done to validate these materials. And in fact, a lot of them are being done, and there's a lot of promising early stage testing on this front, but there still needs to be a lot more done on this. This is one example here of a test where this cell was run for 1,000 hours under continuous operation in simulated sunlight and at elevated temperature. This is to mimic, for example, how it would operate on a rooftop. And some of these cells are really surviving a lot of these tests. And so that's a very good validation that they're on the right path. So this is in terms of what we do in our group. This is our group based in the Chemical Engineering Biotechnology department here in Cambridge. We also have labs in the Cavendish labs in physics as well. So we're a mix of expertise. So we're physicists, chemists, material scientists, chemical engineers, electrical engineers. So we have a wide range of expertise, and this is really needed when we're working on things that span from materials development all the way through to physics, to characterization and advanced characterization, and even through to engineering devices. So it's a really we have a great mix of expertise in the group. We as any group that works with light, we always have a ground state and excited state photo. So this is us in our excited state here. And one of the particular things that we work on is we use laser light and optical spectroscopy to try and understand how these materials work, and where if there's, for example, defects that contribute to power losses, and therefore how we could remove them. So here, this is some examples where we shine light, very fast pulses of laser light to energize these electrons, and then we watch them. We can look at things like the light coming out to watch how fast these carriers recombine, how fast they lose their energy, or how fast they're collected at electrodes. So this is very important information to understand how these cells work and how we can make them better as well. And so one example this is some work, in fact, some of the earlier work in the perovskite field, looking at how far charges can travel in these materials. If you remember back to the cell I showed you at the start, where we sandwich between electrodes as absorber, and we need to collect those electrons in holes. So a really important parameter to know is how far these charges can travel before they lose their energy to heat. Because that tells us how thick we can make the solar cell, for example, or if we need to design the device in a different way. So this is some work where we were, this is looking at cutting a perovskite cell in half and looking at a cross section again. And what we do is we put a pulse of light in at the bottom, and with a very fast pulse that's 100 picoseconds, which is 1,000 billionth of a second, so very, very fast pulse of light. and we watch the light coming out. And so we can look at decays over time. So this is looking at the light over nanoseconds, so over billions of seconds, how that light, how these carriers decay away. And when they decay away, they emit light. And so we can model that using a diffusion equation. So these charges diffuse around, and from that we can extract how far they can travel, because how far they can diffuse. And what we found is that they can travel micrometers in these materials. So when we excite them here, this is, you can see a scale bar here, this is about half a micron in thickness. It means these charges can easily traverse that distance and be collected at an electrode on the other side without losing their energy to heat. So this allows us to design them in very simple ways, where they're just sandwich structures between electrodes. Another thing we do is we zoom in on these materials. We use microscopes to look at the optical spectroscopy of these materials again. And so this is a solar cell put under the microscope, and you can see a perovskite solar cell in particular, and you can see that these cells these materials are actually made of grains. You see these grains are making up sort of a mosaic pattern. That's what you see here. And the color on this map is actually the light coming out. So when we put light in, now we're looking at the light coming out. And that gives us important information, because where we don't have much light coming back out, that means that a lot of, so in these dark regions, sorry, my mouse is a bit slow. You can see where the arrows are pointing in these darker regions, this is where we have lots of losses, lots of power losses, because we have carrier traps. So these energized electrons fall into traps, and then they lose their energy to heat. And so they wouldn't contribute to the solar cell's power. So whereas there's other regions that are really bright and luminescent, and that's good. That means we have very few defects in those regions. So this tells us that we need to we need to design the devices or the materials so we have a uniform and bright image, ideally. And so this is a good technique to be able to assess how good these devices are. We can also do some very interesting techniques where we can actually put them really under the microscope and again excite with a packet of laser light. And then what we can do in these experiments actually is look at these charges trapping in real time. And so this is a really, really cool experiment where we have this. This is actually in an electron microscope, and we can actually see in real time and real space. So with almost nanometer precision, we can see where these carriers are losing their energy to. And so I'm going to play a movie. So this is in picoseconds, so really, really fast timescales. And when at 0 picoseconds, the light comes in and excites these carriers. And what you're seeing in the dark regions here, these are the carriers trapping in the material. These are traps that where they're losing their energy to heat. And so this is a really, really powerful technique to really delve into the nanoscale and see where these materials are losing their power. And so what it tells us is that we need to remove these sites where you have these dark regions. We can also use electron microscopy techniques to understand why they trap in certain regions. And this is some work we've been doing where we can identify these traps, so these losses. So this is on the left here. This is an image looking at these grains, and there's that little blue spot you can see at the center here. That's a trap state that we can identify using these techniques. And what we can look at the crystal structure of these grains. So if we look at the crystal structure of the grains on either side, you can see that one of the grains on the bottom there is actually it's pristine. So when we look at the diffraction pattern of how when we send electrons through, how these electrons interact with the material, we can actually tell what the crystal structure is of these different regions. So on the bottom there, it's a pristine grain, so it's perovskite that we would expect. But on the top there, that pattern actually is slightly distorted. So we actually have a grain that's more defective, and it's at that junction where these carrier traps form. They form in clusters. And so this is really interesting. It tells us it's really these little tiny locations which will be important. And these are actually important not just for carrier trapping, but also for degradation of the material. So as we operate the solar cell over time and operate under sunlight, for example, for many years, for example, these tiny little sites that trap charges are also sites where we start to lose our material, in fact. And so this is some experiments where we can see, so the yellow shading is these sites that are problematic and they're slightly different structures to the perovskite. When we look at them in an electron microscope before and after lots of light, you can see lots of changes to the material at these sites. And in fact, we actually have material being lost here, and eventually they form little pinholes, so you actually lose the material entirely. And this is, of course, not good for long-term operation of a solar cell. We need to get rid of these. So this is telling us a lot of information about how we can understand these cells, and then how we can improve things. And so, speaking of improvements, this is some work where we are trying to improve these, and we're looking at different additives and post-treatments of the films when we make them to produce a better luminescence map. So you can see on the left before and after these treatments, for example, you can see it's much more uniform. It's much more luminescent as well, which is what we're seeing in the color here. So this is improving things and removing some of these problematic traps and defects. And then one of the other topics I wanted to talk about briefly was on scaling up the devices. How can we move them from sort of small area in the lab up to much larger area? And so some work we're doing is not just using solution to process them, so using inks, but actually using vapor methods where we actually have the precursor salts and we actually sublime them onto the substrate. This is called thermal evaporation. So we heat them gently, and then these materials form very uniform layers on the substrate. And this is a technique that can give us very, very uniform films. This is an example here of a flexible film this is a 10 by 10 centimeter example here. And it's very, very uniform. And so this is a technique that is very scalable and could take these cells to much larger areas as well. And finally, I want to give an example of, I told you about space applications and how these materials can be really interesting for using them in space. And one of the really important things to test for these cells is whether they would survive very high energy proton bombardment, which is what you see in space. We're very lucky on Earth that we won't be seeing that, but in space, these cells will see this. So it's really important to do checks to see that they do survive. And so these are some experiments where we actually bombard with protons, very high energy protons, these cells. And so these are proton doses that are equivalent to 50 years in an ISS orbit, International Space Station orbit. So really a very long period and very high rates of bombardment. And when we look at these tandems, this is a particular type of perovskite tandem cell. You can see it's very, very stable and it doesn't degrade after a very high dose of protons. Whereas if we look at something that has silicon in it, this perovskite silicon cell, that degrades very quickly. So we see we see losses in the performance parameters of these cells. And that's because silicon, when you produce defects, that really does kill the cell performance. Again, that's why you have to heat them, produce them at very high temperature. So this shows that these perovskite cells are very, very promising for space applications, and particularly for very long-lived cells in space. I want to finish by just saying a few other applications that we're working on in the lab beyond lighting and beyond solar. One of them is actually looking at Xray, them for Xray detectors. So these materials, so they absorb light very well, but actually if we make them very, very thick, they also attenuate X-rays very well as well. We can actually use them as X-ray detectors for medical imaging, for example. And this is a really growing area and something we're very excited about, to make very high resolution X-ray detectors that could be a lot cheaper than the current systems. Also quantum devices where we can make very small nanoparticles of these materials, and these can actually, we can produce things like single photon emission where we just have one photon emitted at any one time. And this is essentially a building block for a quantum computer. So these materials could be very interesting for some of these applications. And finally, we've got a project with the Center for Global Equality and Bahidar University in Ethiopia to develop mobile solar water pumps using these perovskite cells. So here we have the goal is to have a very lightweight module, PV module that can be moved around, for example, moved around a farm to different boreholes to pump water out. At the moment, a lot of water is pumped manually, so this can really alleviate a lot of these issues, and particularly for the farmers in Ethiopia. Just to finish, I want to give a call out that you can meet our team. So on Saturday, we're hosting in the Department of Chemical Engineering Biotechnology, we've got a stall here where you can actually come and make your own solar cells, making cells, in fact, from berries and from juice. So it's good fun. So please do come out and have a chat with us and visit us. So it's you can register here, and it's running on Saturday from 10, in fact, till 2. So please do come along. And kids are very, very welcome. It's a lot of fun for kids and adults. So please do come along. And I want to finish with a charity organization, in fact, that spun out from our lab, recently founded to produce teaching modules and teaching materials for teachers for primary school age children to teach around not only what climate change is, but also some of the solutions to climate change. So some of the things that we're working on in terms of solar technologies, to really inspire kids that there are solutions for this, and to really get them engaged in this. And there's some hands-on experiments and other things that we've got. We've rolled this out already to around 10 schools around the country, and we'll be delighted to expand that further. If you're interested in finding out more, please do contact us. There's an email down the bottom left there. In fact, we're actually hiring at the moment for an outreach officer. So if you're interested, please do get in touch. So just to finish, these halide perovskite materials are really, the idea is these could take the baton on the current technologies on silicon, for example. We can't stop production of silicon. We need to make sure we keep rolling out as much PV as possible, as quickly as possible, to reach decarbonization goals. But as these other technologies, like these perovskites, come along, they can really feed in and boost this effort. And that's really where the power is in these new technologies. The reason they work so well is they absorb light well, and they transport energized charge as well, and that's really some of their key features. They can be processed at low temperature with very high throughput, so this really does open up new manufacturing regimes. And there's some of the first products emerging, but there are still challenges, and there's still work that needs to be done both in academic labs and industrial labs to really push them forward and to reach their full potential. So with that, thank you very much to my group. It's a pleasure working with some brilliant people here and collaborators around the world as well, and also funding agents. And I'll be happy to take questions and to discuss more on the topic. Thanks very much. And so I think there's been some questions coming in. Thank you, and please do continue to put questions into the Q&A, and we'll start working through them. We've got some from our team on board as well, who'll be helping to manage the questions and make sure we get to everyone's. All right, so I'll start looking through the questions. So I think there was a question here on what do you think about the role of chloride as one of the halides, apart from improving film quality? Do you see any potential applications of pure chloride-based perovskite cells? For example, in Internet of Things applications. So yeah, very good question, thank you. So I talked a lot about iodide and bromide, but there's also, you can put chloride in these materials as well. The chloride in particular opens that band gap up further, so you move to, for example, much more blue emission or even UV emitters. And so there could be some very interesting applications in emission using chloride-based perovskites, particularly for blue LEDs. That's one of the much more tricky colors to work with, in fact, and that has historically been the case in many different technologies. And also potentially for light harvesting in indoor applications where you need there's more blue to harvest and you have less of the near infrared. The tricky things about chloride is with the perovskites that they don't form as well in terms of the films and the performance. A lot of the defects that are there, they seem to be more problematic. So there is a challenge there to implement them. Okay, so next question. So are there any long-term failure or wear-out mechanisms which need to be resolved before this technology can be widely deployed? Yes, thank you, very good question as well. So yes, in the short, there are things that still need to be worked out, and hopefully I gave you a flavor of that through some of the work we're doing. So the cells at the moment, they're not ready to last for 25 years on the rooftop. There has been some very good demonstrations of at least multi-year, 1 to 2 year testing of the cells, but they've lasted that long. one of the issues is we haven't yet been able to test them for long enough to know how long they last. And the second is that what has also been the case for other PV technologies is that there's failure mechanisms that only really come up multiple years into their lifetime. There are different failure mechanisms that we may discover as things go along. So we do have to continue to test these, particularly with accelerated tests, where we can really try and mimic many, many years of operation with elevated temperature, for example, or elevated sunlight levels, to really try and mimic a very long lifetime. But there's still some issues to work out, hopefully over the next few years, that we'll be able to get rid of these. Okay, so there's a question on how long is the registered charge trapping, detrapping in picoseconds. So it's a very good question. So the trapping process, so if you remember that video I showed earlier on, the actual trapping process, so how long it takes for a carrier to be energized and then to trap, it's less than 100 picoseconds. It's somewhere around 60 picoseconds or so. So it's a very fast process. If these traps are there, they will these carriers will see them and will hit them. Okay, so there's a question on how long would it take for market reality? How long will it take for so perovskite tandems? Well, I think so first of all, how much time does it take to hit the market and to really hit the market? It's a very good question. So the first that I showed a couple of examples of pilot lines and manufacturing lines of companies that are starting to produce the first product. So I believe Oxford Photovoltaics, for example, have this year earmarked as their first products coming out. Those are perovskite silicon tandems, where they're perovskites on top of silicon. But of course, they'll start, of course, at smaller scale. How long before it hits, really, I suppose, how much before it competes with current silicon technology? The reality is it's probably 5 years before it hits, serious volume, and probably a decade before it really gets to the volumes and the costs that really properly compete with silicon. So these timescales are compatible with what we need for these new technologies to come online, but we do need to accelerate them as fast as possible. Okay, so there's a question on what is your range of predictions for solar power installed by 2030? Very good question. So what we need is that rate to be around a terawatt per year by the end of the decade. That's very ambitious. That's something that I hope we can still hit, but it does mean a very large increase in the rate of deployment. I think we're about to hit the first terawatt, and that's a very important milestone in terms of PV, in terms of how much we've deployed. But the next terawatt has to come quicker than it has so far. I think we'll be hitting at least another terawatt, or possibly even to 2 to 3 terawatts by the end of the decade, and that would be a very good thing. But that's still probably not enough. We do need to be doing more than that. Okay, so thank you for the questions. Keep bringing them in. So there's a question on, are perovskites really scalable as they have lead, which is toxic, and other metals which are not as abundant compared to silicon? A good question. So first of all, on the lead, so yes, they do contain lead. There's when we think about the amount of lead in these materials, so they're very extremely thin film materials. In fact, it's an extremely small fraction of lead, extremely small absolute amount of lead. And even actually, if the whole panel failed and all of the lead washed off into the soil, it would still be well below the safe level. It'd be well below the safe levels of lead in the soil. That's not to say that this doesn't need to be considered. It's very important. It does, and in fact, what is most likely going to be very important with these technologies is, in fact, thinking about the full life cycle of them and having so being able to really package the cells well so that they don't fail, and if they do fail, and that the lead can be captured and doesn't leach out, and also thinking about end of life. Where do they end up at the end of their life? And it'll be really important to think about recycling and recovery models for these as well. Some interesting progress has been made on this. There's some very interesting developments on lead sequestering agents on these cells. So putting things like lead sulfate, converting to things like lead sulfate, so that when if the cell fails, for example, the lead is quickly immobilized and is not soluble, for example, and therefore won't even get to the soil. So there's some really advanced engineering processes that can actually mitigate a lot of these issues. In terms of the elements that are there, so all of the perovskite absorbers, they're all earth abundant elements. That there's no issues in that sense. There's in some of the cells we use ITO, indium, for example, but there's no reason for that. So indium is very scarce. That's something that will be a problem. Also for the display industry, in fact, that uses a lot of indium, but that's not necessary. That's for just for a transparent conducting oxide. We can use other alternatives, and there's some very interesting alternatives, for example, carbon-based alternatives as well. So that's not an essential element of the cell. Okay, so a question on so on Swift Solar. So from a business perspective, I'm interested as to why we set up Swift Solar in San Francisco and not in Cambridge. This is a very good question. So I was, in fact, before my position in Cambridge, I was at MIT in the US, and in fact, the founding group actually got together there. There was some of us at MIT and some of us at Stanford, and that was the right place to start it. So we ended up starting in California. We actually did a lot of work at NREL as well in Colorado, which is where the National Renewable Energy Labs are. So there's lots of good infrastructure there. We also found there's at least from an investment point of view, there's good appetite for hardware investment in the US as well. So there's a good environment for that as well. I'm still quite heavily involved, even though I'm based in Cambridge in the UK, and we have obviously a lot of our research group. What we do is very relevant, but I also am quite actively involved as an advisor in the company as well. A little bit harder with the time difference, although with the COVID times, things moving online actually made it compatible with working there. All right, so there's a question on the slides that you showed about the effect of defects on the performance of the device. Could you please explain more about what type of defects particularly affect charge traps? And so that, for example, some of the data I showed a distortion, but can we actually say what type of defect it is? That's a brilliant question. Thank you for that. It's quite different. So what we can see in these materials that we see a certain structure, for example, that is not perovskite. That doesn't tell us that we know what type of defect that is. What we have, we work closely with theory collaborators who can model the electronic structure of these materials, and for example, they can perturb the crystal and see how that would affect the different states that are there in the material. And what we believe is that these slightly distorted structures, these different phases, for example, they actually have very high defect densities of particularly what's called interstitial iodide. So we have an iodide that's sitting in between the lattice, in fact, in between atoms. And that, if we have an iodide sitting there, that introduces states in the band gap. And that's where these charges are trapping. That's what we believe at the moment. That's the sort of the leading thought. It's still very difficult to experimentally verify exactly what type of defect it is, because it's very difficult, especially in these small regions, to see an iodide defect itself. We're starting to actually push towards some more atomic scale imaging as well, which is we're hoping to be able to see more of these directly. Okay, so there's another very good question on what do you think is the main limitation for perovskite LEDs to reach the market? And this is a very good question. I talked a lot about the commercialization of solar cells and perovskite solar cells, and that's partly because the solar developments are more mature. They started earlier, and the perovskite LEDs are really probably about 5 years behind the PV developments. One of the real issues with LEDs is you have to run very high currents through them. So especially if you want to get to high brightness of an LED, and much higher, for example, than the currents in a solar cell. And so this is actually quite an issue, because when we run very high currents, we do get some degradation processes that happen. And things like when we run lots of current through them, we have ions that can move in the material as well. And these can lead to more defects and also to degradation pathways. So it's at the moment, it's very tough. A lot of these LEDs are really, the perovskite LEDs typically last for minutes. There's been some reports of hours, but we're not hitting the tens of thousands of hours that LEDs would be rated for from commercial technology. So there is still a long way to go. I think there's still a big challenge of how to solve, when you run high currents through these materials, how to stabilize them. And that's something that I hope over the next few years that we'll make some good progress on, both in our lab and in other labs around the world. Okay, so there's a question on what are the factors that determine VOC. So and maybe so if we think generally about solar cells, so that the open circuit voltage is it's a key parameter in the solar cell. It's mostly dictated by the band gap. So as you go to a wider band gap material, you get a higher voltage, a higher open circuit voltage. If you remember, I talked about the compromise that we want to make that band gap lower for current, but higher for open circuit voltage. So there's some compromise between the two. The things that affect voltage, particularly, are these defects. So when you lose the energy of the electrons to heat, that lowers your open circuit voltage. And in fact, that's when I showed those maps where you have little dark spots, that directly impacts the VOC. You have a drop in the VOC because of that. Okay, there's a question on how near do you feel you are to plateauing to improving the performance of perovskites? Yeah, another good question. So when you look at the efficiency charts, it certainly has slowed, and that's understandable because we're now pushing towards very high values and not far off the limits. I mean, I think that we still are seeing increases. I mean, in the last year, it's gone up almost 1% in absolute terms, and I think we'll see probably another percent over the next year, maybe over the next 18 months. So I wouldn't say, so it's slowing, but I wouldn't say it's stopping yet. It's not fully plateauing. In the tandem cases, the tandem efficiencies are still lower than they could be. I think the trajectory is still a bit higher, and we will still see further increases there as well. Okay, so there's a question on, what do you think is or would be the limiting factor in terawatt scale deployment of perovskite modules? And yeah, another very good question. So, I mean, to hit terawatt scale, well, first of all, for the perovskite technologies to compete, they will need to be shown to last, for at least decades. And there's certain models that show that even 5 to 10 years will be enough needed for market entry. So there's that aspect that they do need to hit R&D milestones before we're releasing them at scale. In terms of the terawatt scale, so provided the specs can be met in terms of efficiency and stability, for example, and reliability of the cells, there's actually very little stopping it from hitting very high rates because factories can be built faster. They can be more modular. You can have smaller scale factories even in more places. It does open up a lot of very exciting opportunities to very quickly ramp up, provided these R&D goals can be hit first. Okay, so there's a question of, do you see any future of solution process perovskites given the current solvents are not allowed industrially, or do you think the future lies more in thermal deposition? Very good question. So traditionally, some of the solvents that have been used, so dimethyl formamide, for example, some of these have been can be quite toxic and they're more difficult to use industrially. There are some very interesting, much more, as they call, green solvents being used and adopted that are looking very promising, and there's a lot more work going on in that space that these solvents that are much more green and much more environmentally friendly and less toxic are starting to hit very good efficiency values as well. So I think from that perspective, I see solvents can be solvent-based processing can be very competitive, because this also opens up things like slot die coating and even inkjet printing of these cells, which is very scalable and can open up a huge area. But in terms of solution versus vapor, it's a very interesting question. But at the moment, different companies are following different avenues, and both seem to be viable. So I wouldn't say there's a clear answer right now. And in fact, I would say both would be viable and may appear in different places. Vapor can be useful if you're processing on something that you can't use solvents on, for example. But I think I would say the jury's still out on which might win out. In fact, in many ways, both are viable. Okay, so there's a question on which type of perovskite material you think will strike the market in the future. So this is there's some different compositions, so methyl ammonium lead iodide, formamidinium lead iodide, or other mixed ones would strike the market in the future. So yeah, very good question. There's the earliest days of the perovskite solar cells mostly use the methyl ammonium cation. This one's quite unstable, in fact, and a lot of the earlier cells were unstable because of this. The more recent configurations and those that are really hitting the highest efficiency levels, these are using formamidinium lead iodide or mixtures of formamidinium and cesium, and these are much more stable and much higher performing. I think these will be much, those will be the future of the cells, particularly the formamidinium lead iodide systems. I don't think methyl ammonium is going to be, it will be thermally stable enough to really be commercially viable, although there are still cells that are working well with that configuration as well. So I would say the formamidinium systems or slight mixtures of them will be there. Okay, so I think we're running out of time. Maybe I'll take one last question. So there's a question on what are the mitigation approaches to have stable perovskite devices? Yeah, very good question. So this is when we're thinking about stabilizing the absorber layer. So if you remember, I showed some of these small impurities that are really problematic. And there's some very promising additives and passivation approaches that can mitigate defects. So these are chemicals that we can add that either convert these unwanted phases to other things, or that can interact with these iodide interstitials and make them benign. These seem to be a very promising way to get rid of these traps, but also stabilize these cells as well. Yeah, so I think going forward, there's going to be some really interesting work to really stabilize some of these, to really get rid of these small impurities that I've showed, and they'll need to be not only sort of got rid of in the lab, but also on the manufacturing line. If we're making roll-to-roll huge sheets of these, then we need to be able to get rid of them even on the large scale. Okay, so I think we've hit time. So I'd like to say thank you very much, everyone, for coming along. I hope you enjoyed that. Please do come along on Saturday to meet us and to chat more, or send us an email. And thank you to those who put in questions. There's some very interesting questions and discussion there.